Okay. We covered section 1.1 well last week. It was kind of a longer section with a lot of introducing, but this section 1.2 should go pretty quick, I think. We'll see. Sure. At the end of class, I'll leave some extra time if you want to do the introduce yourself, just so we can make sure that your camera works and everything. We could do that at the end of class, or you could come to my office hours or set another time up. So this section is mainly scientific notation. When you have really large or really small numbers, instead of having to put all of these zeros, we can rewrite it. So one way of rewriting, if we look at this number, 1,000, million, billion, trillion. So it's actually 1.4 million trillion. So then you're putting two large ones together rather than just saying trillion or million. It is so large that we'd like to find another way of simplifying it. And so what we can use is powers of 10. 10 to the first power is just 10. 10 squared is 10 times 10 or 100. 10 cubed, 10 times 10 times 10 is 1,000. Notice the cube, or whatever the exponent is, that's how many zeros there are. So 10 to the fourth would have 4 zeros. 10 to the 10th would have 10 zeros. It's however many units we're moving, and in this case, it's just the zeros. The number 8 million is 8 with 6 zeros. So it can be written 8 times 10 to the 6th, because we know 10 to the 6th will be 6 zeros, which is what we needed, times the 8. A number is written in scientific notation if it is expressed as the product of two parts. This is the one part times the other part. An ordinary decimal number called a significand, like 8 in the example above, the decimal has to be between 1 and 10. It cannot equal 10. So it has to be between 1 and 10. A power of 10, like 10 to the 6th in the example, the power to which 10 is raised is called the exponent. So in this case, the 6 is your exponent. If we look at this number, then we need, I don't think I put it down here. You need to get a number between 1 and 10. So you have to decide where you can put your decimal so your number could be between 1 and 10. If we put it here, that's 14. It's too large. But if we put it here, then I have 1.4. That's a number between 1 and 10. No, you're not just counting your zeros in some cases, because we also want to move this one to the 10th position. So it's your, think of it as your units or your spaces. So your decimals here, you could count how many you move it. 3, 6, 9, 12, 15, 16, 17, 18. I need to move my decimal place from here 18 units or 18 positions to get it here. So it's 1.4 times 10 to the 18. After we go over these larger ones, we'll do smaller. So this 18 could be positive or negative. Now the book has a rule in there, when you move your decimal to the left, your exponent is positive. But then when you're going back, you got another rule to remember. I like to think of it as this is 1.4. If this is positive, this will get bigger. So we want it positive, so 1.4 gets larger. If we wanted it to get smaller, then we want a negative exponent. It takes away spaces. Let's try a couple. So write this number in scientific notation. Two. So we want to put our decimal here. So we have a number between 1 and 10. So it's 2 times 10 to what power? Getting 18. 3, 6, 9, 12, 15, 18. Any questions on that? Okay, go ahead and try the next one. We're going to put the decimal between the 1 and the 5. So we have a number between 1 and 10. Three, 6, 9, 12, 15, 18, 19, 20. So you get 10 to the 20th.
I also see that there's that cubed notation after the M.
Okay, that's just meters cubed. So we
Okay.
could have units there. The first one didn't have units, but the second one did. Just like this one has 93 million miles. So this was just meters cubed.
Okay.
Any other questions? Okay. Number 3, 98 million, and then miles, we're not, yeah, we do need miles because we're going to convert to inches first and then write it in scientific notation. So you want to take 93 million miles, convert it to inches, and then rewrite it. So we need to convert to inches first and then scientific notation. I do not know miles and inches, but I know miles and feet. How many feet are in a mile? And if you don't want to,
5,280.
thank you. Yep, 5,280. You can always just type it in the chat also if you don't want to say, so then I know more people know it also. Or if everyone unmutes and says it, that works too. So there's 5,280 feet. That is one you definitely want to memorize. Now, do we want to put, because we want the miles to cancel. So should I put miles on top or bottom?
Top.
Okay. Notice if I put it on top, they're not going to cancel. So since the first one is on top, I need to put this one on the bottom. That way they will cancel. And then we have 5,280 feet. From feet, we can go to inches. How many inches are in a foot? Anyone?
12.
12. Now, we know 12 inches in a foot. When we write our proportion, we want this foot to cancel. So should we put foot in top or bottom on the second one?
Bottom.
Yeah, that way they will cancel. So by putting this on the bottom, the feet cancel and I'm left with inches. It also lets you see that you want to multiply across the top, which means I'm multiplying by the 5,280 and multiplying by the 12 instead of dividing.
What is on the bottom under the 12 inches? I can't really read
Oh,
it.
sorry, 1 foot.
Thank you.
You're welcome. And then this foot will cancel with this one. So on the bottom, we just have ones. On the top, now the good thing is if you're multiplying with your calculator, it's probably going to put in scientific notation for you. So let me make sure I put enough zeros. 1, 2, 3, 4, 6. Okay. And so when you multiply them, this is giving you the scientific notation. This E is just 10. So it's 5.89248 times 10 to the 12th. So that E is just a 12. Now some calculators, I don't have my other one with me, it actually puts a 10 down here. But most of them use an E. That E is just telling you 12 is in the exponent. Any questions on that one?
Could you flip back to that page really quick? I didn't get it.
Oh, yeah,
Thank you.
you're welcome.
Is there going to be any vocabulary of these words, like how the significant, is that kind of stuff going to be on our test though?
Significant digits. I'm kind of torn. I'm not sure yet. That's in the next section or the fourth. It's either in the third or fourth section of this chapter. So I'm not sure. I think I'll have a little bit of significant digits, but like for this problem, if I was going to have you reduce, I would probably say round the scientific notation to the 10th. So then it would be 5.9 times 10 to the 12th. So I would probably do more rounding. There might be 1 or 2 basic problems that use significant digits. The way this is written, all of these are significant. These are not, but we get into that in, I think it's section 4, 1.4.
Okay.
So this one would be write the scientific notation and then round to the 10th. Now these are the negative exponents and 0. 10 to the 0 is 1. Anything to the 0 power is 1. A negative exponent just moves it to the denominator. So 10 to the negative 1 is 1/10. Or, whoops, this is not. This should be 0.1. So I remember to fix that. This should be 0.1. They put a 0 in the front so that when you're writing sentences and things like that, it doesn't look like a period. It's not wrong without the 0 in front of your decimal. I would not take off for 0.1 instead of 0.1. A -2 is 1/100 or 0.01. So notice that it's not counting the zeros now, it's counting the places. This is 2 places when it's a 2, 1 place when it's a 1. If you want to count the 0 in front, then you could count zeros. Technically, the 0 in front doesn't need to be there though. 10 to the -3 then is 0.001. Any questions on that? To express a number less than 1 in standard form, move the decimal point to the right until you obtain a number between 1 and 10. So we're still getting a value between 1 and 10. What you obtain is the significant, and minus the number of steps to the right that you move. Now, you can remember if you're moving to the right, your exponent's negative. I always remember that when I have my significant, if it's getting smaller, then it's a negative exponent. So doing these is the same thing. You first see where you need to put your decimal so you have a number between 1 and 10. So here's my numbers. The only way I'm going to have a number between 1 and 10 is if I put it here between the first 2 and the 3. Anywhere else, it's not going to be between 1 and 10. So I know I need 2.32. Then count how many places you needed to move. So from here, we're moving 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Is that what everyone got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So I needed to move 15 spaces. I think. Should have used something smaller. 3. Okay, 15. But this number needs to get smaller, so this needs to be negative. If this is negative, this will get smaller.
Isn't it technically getting bigger?
This number's bigger. When I go back to the original, I need to get smaller. And so I want to multiply this by a negative. Yeah. So look
That
at
makes sense.
this value. look at this one. If you need it to get smaller, this needs to be negative. So when you multiply, it will become smaller.
Okay, yeah, that makes more sense.
Yeah. Let's try the next one. So first decide where your decimal needs to be. And that would be between the 3 and the 2. Then see how many places you need to move that decimal. 1, 2, 3, 4. And 3.2 needs to become smaller when we multiply. So this has to be a -4. Any questions on that?
Okay, so kind of like a general thing, most scientific notations for decimals are going to be negative.
Yes, absolutely. So if you have a decimal instead of in the integers, like something
Mhm.
greater than 0. So if your numbers are less than 0, all these zeros, it's going to be negative. And when it's a large value, too low. When it's a large value, it will be positive.
Okay, cool. Thank you.
You're welcome. Now these ones are going the opposite direction. They're going to decimal notation. So for decimal notation, you want to do the opposite. You're multiplying these. Now, a lot of cases, if you plug them into your calculator, it's going to give you scientific notation depending on how large it is. But just remember, we're going the opposite. So we have 2.6. We have a +5, so this needs to get bigger. We're going to move 5 units this way so that it gets bigger. $260,000. So that 5 made this bigger by 5 place values. 1, 2, 3, 4, 5. Any questions on that? Now, number 4 has the same thing, but a negative exponent. So instead of making my number large, it's going to make it small. It's going to make it decimals. I'm going to start over here so I can fit it all. So I'm going 5 units to the left. 2, 3, 4, 5. Now you can put the 0 in front, so it would be 0.2, 4 zeros, 2, 6. Any questions on that? Yeah, if you're having any trouble with your internet, it's recording, so it will be up under Media Gallery. Okay, go ahead and try. Okay, I think we're both. Let's make this one negative and this one positive. So the first one, when there's no decimal, the decimal's right after the number. So it's just the number 7, then it'll be point. And the 4 means to make it larger by 4 place values. Because in our numerical value, they're each tens. 1, 2, 3, 4. $70,000. And this one, we're going to make the exponent negative. That way we can see the opposites. This one got larger because it's a positive 4. This one will get smaller because it's a negative 4. 1, 2, 3, 4. Any questions on those? Let's look at number 7. In 2015, in a scandal affecting 500,000 vehicles, the United States Volkswagen was caught using software to cheat on emissions testings for diesel vehicles. Volkswagen diesels were found to emit 1 gram of nitrous oxide per kilometer driven, about 40 times the legal limit. In a vehicle with the software, the emission control systems were fully activated only when the vehicle was being tested. If each car is driven 20,000 kilometers per year, estimate the mass of nitrous oxide pollution that is emitted in 1 year from the 500,000 vehicles. And then write your answer in scientific notation. So the first thing I want to do is start with the, I don't know, something. I would probably start with the 1 gram of nitrous oxide per kilometer driven. Whoops.
So it's asking us for a total of 500,000 of those cars, correct?
Right.
Okay.
If we find out how much for 1 car, then we can multiply by 500,000 to get the rest of it. Well, yeah, I think it's easier that way than to start. You could start with the 500,000 cars.
Okay.
Either way, you should get to the same answer. Well, since I wrote this, I'm starting with this one. But if you want to start with the cars, you could go the opposite direction and we should get the same answer. So if we have 1 gram for each kilometer, and each car is driving 20,000 kilometers per year. Now we need, so we know we have 1 car, 20,000 kilometers per year. So we have to decide, are we putting the 1 car or the 20,000 kilometers on the top of our fraction? Notice this kilometer is in the bottom, so I need a kilometer on the top, so they will cancel because we just want to be left with grams of nitrous oxide. So here, I would put my kilometer on the top and my car on the bottom. That way kilometers will cancel. Kilometers was 20,000. 1 car. And this was kilometers. If you want to put the per year, you could. And then we need, let's see. The 500 cars. 500,000. So my kilometers canceled. And if I multiply by my 500,000 cars, they will cancel. 1 gram times 20,000 times 500,000. 2 times 5 is 10. And then we have 1, 5, 6, 7, 8, 9 zeros. 5, 6, 7, 8, 9.
I got 1 to the 10th.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yep. 1 times 10 to the 10th. Now you could write it like that. The book says you do have to have your significant here. So notice it can be a 1, but it cannot be a 10. So you could have put 1 times 10 to the 10th or 10 to the 10th. This would be proper scientific notation. Technically, this isn't wrong. Thousand, million, billion. So 10 billion grams of nitrous oxide per year. Any questions on that? And number 8. The United States $1 bill is 0.0043 inches thick. Convert this to meters and express the result in scientific notation. So we have to go from inches to meters. And then we need to put it in scientific notation.
(4.3 times 10 to the negative 3rd power).
That would be scientific notation for this one. 4.3 times 10 to the negative 3.
Which one are we looking at?
But they want it in meters.
Um,
So we have inches. Now, I think it's easier to convert to meters first and then scientific notation. But you could do either way. The only thing is, once you start multiplying, then you have to rewrite this because it's not between 1 and 10. So I think it's easier if we stick with inches to meters. But this is correct for inches. Is there any questions on that? Okay, so this is scientific notation for inches. Let's convert to meters first. Oops, sorry. I don't know inches to meters, but I know inches to feet, and then I know feet to meters. So you want to think how you can convert it. I can go from inches to feet to meters. We said earlier, 12 inches is a foot. Now I got to think about if I want inches or feet in the bottom. This inch is on top, So the other inch needs to be in the bottom so I can get rid of them. Which means I need the 12 inches in the bottom and the 1 foot on top. That way then my inches will cancel. And then we know, wait, I'm thinking miles. Okay, so meter, if you think of a yardstick, a meter is almost a yardstick. It is 3.3 feet. Is 1 meter. So it's a little bit larger than a yard. That's another one you should learn. Notice then we're dividing. Now you could take this number, divide by 12, and then divide by 3.3, or you could multiply across first. So our inches canceled, our feet canceled, we have meters. We can multiply across, so 12 times 3.3. If you're comfortable multiplying across first and then dividing, we could do that. The other ones had all ones on the bottom, so I didn't worry about it. And it put it in scientific notation already for me. 1.0 round the scientific notation to the 100th. So if we look at this, after it's in scientific notation, rounding to the 100th, first decimal place is the 10th, this 8 is the 100th. That 5 would round this up, so it's 1.09. 1.09 times, the E is your 10, 10 to the negative 4. Any questions on that?
No. Wait, it'll specify when it wants us to round to the 10th or to the 100th, correct?
Right. Mhm.
Okay.
Yeah, a lot of times I won't have you round, but because the decimal was so large, I would definitely have you round. Any questions on rounding?
No.
Okay, so your decimal places go 10th, 100th, 1000th. The opposite of going this way, 110, or ones, tens, hundreds. Multiplying. We won't be doing too much of this, but it is in there. And if you tried to do it in scientific notation, then this would help. When multiplying or dividing two numbers in scientific notation, we multiply or divide their significance and then add or subtract their exponents. So if we have 10 to the m times 10 to the n. When you're multiplying, and it doesn't have to be a 10, it can be any base as long as they're the same. You add their exponents. And when you're dividing, you subtract them. So no matter what the base is, if you're multiplying, you add the exponents, and when you're dividing, you subtract them, as long as they're the same base. So if we look at the first one, what this is saying is multiply the numbers in front. So 2.2 times 5. Times 10, and then add your exponents, 6 plus 3. Is this still in scientific notation? No, because it's larger than 10. So I need to move my decimal place here so that it's 1.1 times 10 to a power. Here I am losing a decimal place because I'm making it smaller. I'm losing a position. So I need to add it here. So if you're making this smaller, you need to make this bigger. So again, you want to take 1.3 times 2.1. And then these are the same base, so we add the exponents, -2 plus 5. Now when we multiply these two, we get 2.73 times 10 to the +3. This is between 1 and 10. So this is standard form, scientific notation. Any questions on that one? Let's try number 3. So for number 3, go ahead and try that one. Four times 6, you got 24 times 10 to the 17th. So this is, your book calls this scientific notation, but it's not standard scientific notation because it's not between 1 and 10. I've never seen it worded that way before because usually standard notation is the original number, but they call that decimal. So it's just some wording of your book. I will definitely, if I put scientific notation, I want it between 1 and 10. So it should be here. We're moving it 1 unit. 2.1, 2.4. We moved 1 unit. Now, when I move this, I'm making it smaller. So I need to add another place. Here I took away a place value. Here I'm adding it. Any questions on that? Let's try number 4. Again, multiply your numbers. 3.4 times 2.4. And then we add the exponents. And this is in standard scientific notation. It's between 1 and 10. We don't need to change anything. Any questions on that? It's right on here. A cow emits about 0.3 kilograms of methane per day. There are thought to be about 1.2 times 10 to the 9 cows on Earth. Compute the total mass of methane emitted by cows over 1 year. This is per day. So for 1 cow, it's 0.3 kilograms a day. And we want 1 year. So we need to convert to years. We know there's 365 days in a year. Now we got to decide, is the 365 on the top or is it on the bottom? This day is in the bottom, so I need days on top. And there's 365 days in 1 year. So this is the total amount emitted per year for a cow. Well, we don't need a print. This is for each cow. If there's 1.2 times 10 to the 9 cows, I need to multiply by it. Any questions on that? Okay. 1's in the denominator. Multiplying across the top, I can take 0.3 times 365 times the 1.2. So if I take the 3/10, 0.3 times 365 times the 1.2, I get this value. Now, if you wanted to put all those zeros in there, you could. This section was showing you how to use it with scientific notation. So to rewrite this in scientific notation, I need to move 2 places to the left. I need to make this smaller by 2. Since I'm taking away 2 place values, I need to add 2. 1.314 times 10 to the 11. Any questions on that? Positive.